share my screen because I'm not sure I can do that. Okay, is it working?
All right, looks good.
Okay, perfect, so I can start. Now, okay. Hi everyone, my name is Jacopo Talamini. I'm a PhD student from the University of Trieste in Italy. And today I will present to you another work made by our group named Communication in Decision Making, Competition Favors Inequality. First of all,
Okay. Sorry, I thought there was a sound issue. I just had my sound off.
okay. Okay, so first of all, since this is a work on multi-agent systems, let's spend a few words to define them. Multi-agent systems are models in which multiple agents share the same environment with common or conflicting goals. The easiest way to explain multi-agent systems is probably by using examples, and we can pick plenty of them, both from the biological world as well as from technology. For instance, an ecosystem with animals of different species and different rules is an example of multi-agent system. The components that control the driving process of an autonomous vehicle by communicating through a bus are another example of multi-agent system that is valid as well. But what makes multi-agent systems so interesting to us? We believe that the answer is in interaction. So, interactions among agents allow the development of complex behaviors, even in the simplest scenarios. In a multi-agent systems, in fact, the individual behavior affects everyone to a certain extent, to a point where spontaneous cooperation or competition mechanisms may arise even when not explicitly promoted. And this is important. From now on, we will consider interactions in the form of broadcast communication. And in this work, we consider inequality, that we define as the disparity among the agent state with respect to their individual goal. And we wonder under which conditions individual strategies affect inequality among the agents. We consider a very specific multi-agent system, where there are two types of entities, the agents and the resources. Agents are rewarded for collecting resources, and the collected amount depends also on others' decisions. Agents broadcast their current state, which give other agents information on the next state of the system. Agents observe broadcast communication and resources filling, aka the amount of agents collecting each resource. Finally, each agent is controlled by a trainable AI. In this work, we try to answer to two research questions. Which is the relationship between individual and collective reward, and which is the role of communication in such relationship? To investigate these research questions, we have designed three different scenarios with respect to the resources filling. Each scenario is denoted by a different reward function, where each one promotes cooperation, competition, or a mixed strategy. Specifically, the cooperative scenario rewards agents for increasing the number of agents collecting the same resource. The competitive scenario rewards agents for decreasing the number of agents collecting the same resource. And finally, the mixed scenario is similar to the cooperative scenario until the optimal number of agents on a resource is met, and then behaves somehow like the competitive scenario. Agents observe only part of the system state at a certain time t, which we call the agent observation. This observation contains all the resources filling, the agent state, and finally an aggregate of all the communications. The action that each agent can take is divided in two parts. The first part controls the agent preference over resources, and the second part turns communication on or off. The agent state is updated at time t+1 according to the first part of the agent action taken at time t. Specifically, the current collecting resource changes to the action value if the action confirms the previous preference for a resource. Otherwise, the agent will collect the same resource as before. The agent preference over resources is always updated to the last action taken. This is the second part here. We consider each agent as an individual learner with its own policy, which is the function that maps observations into actions, and we optimize those policies using reinforcement learning. Since observation space and action space are discrete spaces, we consider a simple tabular Q-learning algorithm for this task. We experimentally assess the model with 10 agents and 2 resources for 20,000 episodes of training. Since we are interested in investigating communication in decision-making, we have considered 4 different communication strategies. Always communication strategy, in which agents broadcast their state all the time. Optional communication strategy, which is the only one in which communication is actually learned together with the resource preference. No communication strategy, where agents do not interact by any means, and random communication strategy, in which communication actions are chosen at random. We consider also 2 different levels of observability. One in which agents are able to observe the resources fielding, and one in which this is not allowed. Thus, agents are like blind and can rely only on communication to take actions. This figure shows the overall reward during the training in all the different settings. We can immediately see that always communication strategy is the best one in all the scenarios, even in the one with non-observable feelings, which means indeed that communication is necessary to behave optimally, especially when agents are blind. Surprisingly, the optional communication strategy is optimal in the cooperative non-observable feeling, this one, in the upper left plot, but not in the competitive scenario in the bottom, at the bottom. Looking closer at the individual reward distribution in the competitive scenario for the optional communication strategy, we can see that few agents achieve higher individual reward, even higher than in the other strategies, whereas the majority of the agents perform badly. This scenario is indeed denoted by high inequality among the agents. We can see the same results from a different point of view. In this table, we show the validation results for the optional communication strategy in the cooperative scenario, where each line is the sequence of actions taken by an agent during the first step into the game. The circles here indicate that the agent is confirming its preference, whereas triangles indicate a change in preference. Blue symbols indicate that the corresponding decision has been broadcasted to the other agents, whereas orange symbols indicate that that decision was not communicated. In this case, we can see that there are many blue circles, and this means that agents often communicate when confirming their preference. This is a useful information for the other agents to guess the next system state. So, in other words, agents develop a cooperative behavior by letting the others know their strategy, because letting the other know is profitable for them, individually profitable. On the other hand, the optional communication strategy on a competitive scenario shows few blue circles. Most of the time, when confirming their preference, agents do not communicate with others. In a competitive scenario, agents find it profitable not to tell the others their strategy, or even to tell pointless information, thus resulting in a high inequality scenario. So, to conclude this presentation, we have considered a simple resource collection multi-agent system, where communication is needed to behave optimally. we have trained agents with different communication strategies. And the experimental results show that agents employing optional communication strategy in a cooperative scenario use communication as a way to reduce inequality, whereas in a competitive scenario in which each one promotes its individual goal, communication is reduced, and high inequality lies among the agents. That's all. This ends my presentation. I want to thank you everyone for listening, and feel free to ask a question if you're interested.
All right, great. Thank you so much for your great talk. Again, if anybody has any questions, please feel free to raise your hand on Zoom, unmute yourself, whichever you prefer. Okay, there's a note in the chat asking if you can pull your camera.
Yeah, I've seen it.
Okay, cool.
Let me put this one is the last slide.
May I ask a question?
Yeah.
Sure. Can you? This is really interesting work. I come from kind of a management and organizations background, and we see a lot of these kinds of interest in these kinds of topics in strategy and the kinds of dynamics that we see in those spaces. So I'm curious, what are the literatures that you draw on for your work?
Yeah, this is a really good question because we had to study a lot before starting off this work. But there are many sources that we interrogated. We started from an ecological point of view, first of all. Then we saw that what we were building was even close to resource allocation in the, I don't know, in the industrial ground. And so it's a work that it has no direct implications, in the sense that the ecosystems and the scenarios that we have designed are really abstract. But you can imagine them as I don't know, any practical application you can imagine of. I mean.
I think that that's really interesting. So I think that there may be some practical applications, and that's one of the things. One of the challenges in the space that I come from is how can you take abstract models like these and then use them for things like theory building, taking them and using them as ways of identifying kinds of phenomena to look at in other studies, and then can we identify ways of then using that information to design new mechanisms to improve things like equity in organizations and in society more broadly. So very interesting. Thank you. We should talk more offline.
Yeah, sure. Thank you for your question.